Good day to all. Today I am going to present a topic, geometrical mean radius or GMR and geometrical mean distance GMD, a topic related to power system, and these two terms are using for the calculation of transmission line inductance and transmission line capacitance. My name is Dr. Ismail C., retired professor, Government College of Engineering, Kannur. So we'll be moving to the topic. The expansion of GMR is geometrical mean radius. This GMR is also known as self-GMD or self-geometrical mean distance. Both are same. And this is represented by the symbol ds. Geometrical mean radius, as the name indicates, represents the radius of a transmission line. If more number of strands are there, then the equivalent geometric mean radius. We all know that the inductance of a transmission line per conductor in a single phase system or in a three-phase system is given by L is equal to 0.5 plus 2 logarithm d by r into 10 raised to minus 7, where d is the distance between the transmission line and r is the physical radius of the transmission line. This formula has two parts, one constant part and another variable part. Actually, the first part of this equation, that 0.5 into 10 raised to minus 7, represents the inductance of the transmission line due to the internal flux contribution by the conductor. So we are going to implement or going to introduce a concept GMR for the elimination of the first term, so that our equation will be very simple. Now, how we are removing that 0.5 into 10 raised to minus 7 from this equation of the inductance? For that purpose, we are replacing the solid conductor by an equivalent hollow conductor with a very thin surface. Once we are replaced our solid conductor by such a hollow cylinder or hollow conductor with thin surface, the flux inside the conductor will be 0, because there is no current flows through the inner portion of the conductor. If there is no current flows, means there is no flux inside the conductor. Only flux lines are there outer portion of the conductor. Hence, there is no internal flux. Thereby, we can eliminate the term 0.5 into 10 raised to minus 7. We can see the same concept through these figures. Suppose the current flows through the solid conductor, then the current will be flowing through, we will consider as current will be flowing through each portion of the solid conductor, small portions. So there will be flux lines around all that small portions like this. That will be what the idea is. There will be flux lines inside the solid conductor. But if you're changing that solid conductor into an hollow conductor, then there is no current through this inner portion. Only current flows through the outer portion of the conductor. Now we are again considering that hollow conductor has a very thin surface, so that the entire inner portion has no current. Since there is no current, means there is no internal flux, or the internal flux inside this conductor will be equal to 0. Hence, the effect of magnetic flux linkage, there is no magnetic flux linkage, hence there is no inductance associated with the inner portion of the conductor in the transmission line. So that we can simply eliminate 0.5 into 10 raised to minus 7. Now we will see what is the comparison of this radius. The hollow conductor radius is usually less than the solid conductor radius, since the additional space allows external flux to balance the effect. That is, for the solid conductor, suppose let the radius of the solid conductor, let it be r, then we can see that the equivalent radius will be always less than that physical radius, and by mathematically we can prove that will be equal to 0.7788 into r. Now we will see what is the effect of this GMR on conductor parameters. Before going to that, by eliminating the first term in the inductance equation, the equation will become very simple. That is L into 10 raised to minus 7 ln d by ds, where d is the distance from the one conductor to the second conductor in a single phase case, and this d is the equivalent distance, or again GMD of the three-phase transmission line, that we will explain later. But ds is the GMR or self GMD, which is given by 0.7788 into r dash, where sorry, there is no r dash, this is r only, it's a mistake. 0.7788 into r, and ds is usually represented by that r dash. So by checking this equation, we can say that GMR is only depends on the radius of the conductor. That means it depends on the shape and size of the conductor used. Does not depend on the spacing between the transmission lines. Now we are moving to the next concept, GMD, or geometric mean distance. GMD is also known as mutual GMD. As I mentioned earlier, GMR is also known as self GMD, and GMD is also known as mutual GMD, because this is the distance between different conductors. That is, in a single phase case, it is the difference between phase and neutral, or the two conductor and the return conductor. In the case of a three-phase, it is the equivalent distance between the three conductors. By using GMD, we can simplify the calculation of mutual inductance between bundled conductors. That is, we all of us know that in EHV systems or in extra high voltage systems, instead of a single conductor, we are using bundled conductors. Either it may be a 2 subconductor bundled conductor, 3 subconductor bundled conductor, like that. So what is GMD? By definition, GMD is the geometrical mean distance between one conductor and another. It is again called GMD, and it represents the distance between conductors. Since it is a distance between different conductors, it varies with the conductor arrangement. That is, in the earlier case, GMR depends on shape and size, but here it mainly depends on the distance between the conductor. That is by changing the conductor arrangement, GMD will also change. Now we will see the GMD of different conductors under different conditions. First, we will consider the case of a GMD of two adjacent conductors in a single phase line. Consider two conductors placed adjacent to each other. So in this case, the mutual GMD or simply GMD is the distance between centers of the conductors. That is here only one distance, hence the GMD is the same distance between that conductor. Now we'll consider the second case. It is the GMD of a single circuit of a three-phase transmission line. Single circuit of a three-phase transmission line. Here, there will be two cases we have to consider, either a symmetrical three-phase line or an unsymmetrical three-phase line. Then one more classification is also there that we will see in the next slide. So in symmetrical three-phase line, the conductors are placed on the equilateral triangle and they are placed at the same distance between one conductor and the other two conductors. But in the unsymmetrical case, the distance between phase R and phase Y and phase Y and phase B and phase B and phase R are different. Usually that distances are denoted by D12, D23 and D31. So in both cases, the mutual GMD is equal to the equilateral spacing between the conductors. We will see the formula for both cases in the next slide. For the symmetrical three-phase line or in unsymmetrical three-phase line, the formula is same. It is the cube root of the product of the distance between the conductors. Now, in the first case, as I mentioned earlier, the distances are D12 equal to, let it be D, D23 is equal to again D, and D31 is also equal to D. That means they are placed at the equal distances and or the corners of an equilateral triangle. Therefore, GMD is equal to cubic root of the distances between R and Y, that is D, the distances between Y and B, that is again D, and the distance between B and R, that is again D. So by calculating, we can see that is the distance between any one of the transmission lines. That is, the GMD of a symmetrical three-phase line is equal to the distance between any one pair of transmission lines. If we are applying the same formula to the unsymmetrical case, this is the formula, or GMD of a unsymmetrical three-phase line is equal to cubic root of D12 into D23 into D31. That this mutual GMD is equal to the equivalent equilateral spacing between the conductors of the line. Now, as I mentioned earlier, this configuration, either in three-phase transmission line, either we can place as an horizontal configuration, or we can configure as a placing at the triangular configuration. In both cases, this formula is valid. That is, mutual GMD is equal to cubic root of D12 into D23 into D31. Now, we'll be moving to some numerical problems to make the idea more clear. So the first problem is for a single phase line. That is, it is a two-wire transmission line of 15 km long. It's made up of round conductors. Its diameter is given is 0.8 centimeter. They are separated by a distance of 40 centimeter. So we have to calculate what is the GMD of this particular configuration. So first, we have to note down what are the parameters given. Diameter of the conductor is given, D is equal to 0.8 centimeter. But we require radius, so we calculate radius D by 2, which is equal to 0.4 centimeter. Now, what is the distance between the conductors? That's also given. That is given by D is equal to 40 centimeter. That is also given. Then the 50 kilometer long, that is not required for us for this particular calculation. Now we can calculate geometrical mean distance. We already understood that in a single phase case, it is the distance between the transmission lines. No calculation is required. So GMD is equal to D, which is equal to 40 centimeter or 0.4 meter. Now moving to the next numerical problem. It is a three-phase line, but only using single circuit. So 68 Hertz transmission line consists of three conductors arranged in equilateral triangle configuration with legs 5 meter each. In this case, we have to calculate the GMD of the distance. In this case also, one unwanted data is given, that is a frequency. In the earlier problem, total length of the line is given, that is not required for the calculation. Similarly, here 60 Hertz is not required for the calculation. For a three-conductor triangular configuration, we know that GMD is equal to cubic root of D12, D23, D31. Now, simply substitute the value of 5. So, cubic root of 5 into 5 into 5. Then that will be equal to 5 meter. Actually, we already studied that in a this is a symmetrical configuration, three-phase system. So, in symmetrical configuration, the GMD is equal to the distance between any one pair of the transmission line. Now, moving to the next problem. It is again a three-phase system where, again using a single circuit, there are two cases in a three-phase transmission line system we are adopting. That is either a single circuit or a double circuit. So here again it is a single circuit system. Here the distances are different. That is an unsymmetrical configuration. First distance is 5 meter, maybe 1 and 2. Second distance is 5 meter, maybe 3 and 1. Then 8 meter, that is between 2 and 3. So here the formula, we can directly use the formula cubic root of D12, D23 and D31. So you just substitute the values of distances in the cubic root. Instead of writing the cubic root, I am writing all raised to 1 by 3. So I'm getting GMD is equal to 5.85. So problems are very simple. Moving to the next problem. Till now, we are done problems on single-stranded conductor. Now, we are going to, this problem is is using bundled conductors. We all know that bundled conductors are used for improving several factors of the power transmission line. Here in bundled conductors, as I told earlier, there may be either minimum 2 number of conductors will be there, then only it will be a bundled structure. So here we are using two subconductor bundled conductors. So for one phase, such two conductor is required. Here I am representing my R phase by that subconductor. Similarly, for my Y phase, that is again 2 conductors, and my blue phase, that's again another 2 subconductors. And as given in the problem, that distances are given 5 meter and 5 meter, and the total distance between 1 and 3 is 10 meter. Now we will see how to solve. So to solve it exactly, we have to consider distance between each subconductor. So here I am considering now only my R phase and Y phase. So I'll be calculating the distance between first subconductor of R phase with the first subconductor of the Y phase. That will be 5 meter. Similarly, the first subconductor of the R phase and the second subconductor of the Y phase, the distance is 5.3. That is, I have to add 15 centimeter this side and 15 centimeter this side. So total it will be 5.3. Now, the distance between second subconductor of the R phase and the first subconductor of the Y phase, that is only 4.7 meter. And we can finally understand that the distance between the second subconductors of R phase and Y phase is again equal to 5 meter. So to find the equivalent mutual distance of this bundle to bundle, that is between this R phase and Y phase, we have to find out the geometric mean of this 4 distances. That is, there exist 4 distances between R bundled conductor and Y bundled conductors. So these are respectively 5, 5.3, 4.7, and 5. So there will be so there are 4 distances. That means we have to find out that particular route. That is, if only one distance, there is nothing to mention. Or if there are 2 distances, usually there is no case like that. 2 distances. Minimum, it will be in 2 distances. There is no case. And in 3 distance, we have to find out the cubic root. And for an n distances, we have to find out the nth root. Or we have to do all that distances multiply raised to 1 by n. So here a total of 4 distances. So that is why we are finding out 4th root, or we have to multiply by 1 by 4. So by doing that, I'm getting an answer for 0.99549 exact value. And you can see that if you do the same calculation with the Y phase and B phase, the distances, that 4 distances within YB, first Y and first B, and first Y and second B, These are symmetrical. That means that DBC, actually in my notation, in the figure I am using RYB, and in my formula I am using ABC. Okay, so no need to calculate it again. We would be getting the same result for the case of Y and B. The mutual equivalent mutual distance between Y and B is again equal to 4.99. Now we will see the equivalent distance between the first conductor or first bundled conductor and the last bundled conductor, that is R and B. For that, we can write the distances as earlier, that is the first R and the first B, then first R and the second B, the second R and the first B, and the second R and the second B. So the distances are, if you are writing the distances, it will be 10, 10.3, 9.7, and 10.7 meters. So if you do the similar calculation, that is, we have to find out there will be 4 distances. So you go for that fourth route. So if I'm calculating using a calculator, I'm getting 9.999. So we got all the mutual distances between bundled conductors. That is, we already calculated between R and Y and Y and B. In this slide, we have calculated between R and B. So we have 3 distances now. So what will be the GMD now? So it is the cubic root of these distances. What are the distances we calculated earlier? These are the distances. So if you do this, you are getting it 6.29535 meter. Now, in the problem, nothing is mentioned about the orientation of the conductor. That is, whether it is horizontal like this or vertical like this. That is one thing. The second thing is, compared to the radius of the conductor, the distance will be very, very large. Hence, we can neglect that addition or subtraction of the radius in the original distance. If you are doing like that, we can simply calculate GMD is equal to cubic root of DAB into DEAB. Here I made a mistake. DAB into DBC into DCA. So that is equal to 5 into 5 into 10. It is equal to 6.3. So you just compare the result using the actual calculation. The difference is very small. That is, in this case, for up to two decimal places, it is 6.29. Here it is 6.3. So it is very more or less same. That is, by this approximate method, that is, we can neglect that resistance with respect to the distance between the conductors. We are getting almost the same value. Now, you can consider a problem that there is a transmission line which uses bundled conductors. That bundled conductors are having 3 subconductors, and that 3 subconductors are on the corners of a equilateral triangle. And here also three conductors that are on the corners of a triangle. And suppose this is R, suppose this is Y, and in B phase also there will be three conductors that are placed at the three bundled conductors that are placed at the corners of an equilateral triangle. And suppose that the distance between these bundled conductors are again let it be D, that is, this bundled conductor itself are placed on at the equilateral triangle. That is the in bundled conductors, their subconductors are placed on a small equilateral triangle, and this one, that is the bundled conductors, are placed on a big equilateral triangle. You try to derive an expression for the GMD. I am giving it as a drill problems to the watchers or viewers. Thank you.